maybe if there's some. Greetings and welcome, friends. Here we are. We're taking a look at page 428, we'll call it. We were talking about basic trigonometric identities, and here's question 41. It says, express each value as a trigonometric function of an angle in quadrant 1. So quadrant 1, the key idea there is we can kind of think of these in terms of reference angles here. So here we are, 10 pi over 3. Now, I don't know if you guys know where that angle is, but let's try to figure that out. Now, let's see. 1 pi would have been 3 pi over 3, right? 3 pi over 3 is 1 full pi, which is halfway around a circle, right? So, so there's halfway, would be 3 pi. 6 pi would have been a full revolution. 9 pi would have been 1.5. And then 1 pi over 3 more than that. So I'm thinking it's in this quadrant. Yep. Or the thing that I could do is, let's try to break this down a little bit. So 10 pi over 3, the thing that I mainly wanted to realize was it was bigger than 1 full revolution. So I'm going to subtract 2 pi from this. Okay? And in order to do that, I'll need a common denominator. So I'll multiply this by 3 over 3. So I'll have 10 pi over 3 minus 6 pi over 3. And that's 4 pi over 3. Yeah, so I'm trying to find a coterminal angle with it, so I'm not working with a really large angle. I'm working with one that I can more easily work with here. So what we've got is 4 pi over 3, graphically speaking. As I said, 3 pi over 3 is 1 revolution, so 4 pi over 3 is, 3 pi over 3 is 1 halfway around the circle, so an extra third pi would look something like this. So here's 4 pi over 3. Right? And if I want to find the reference angle, that's going to be this angle here. So how could I find that reference angle? Well, that reference angle, if we call it alpha, would equal 4 pi over 3 minus what? 3 pi over 3? Yeah, or what she's getting is a single pi, right? Subtracting this much would give me what's left over, right? So, so we could call that 3 pi over 3 if we wanted to make things easier. So alpha is going to be a pi over 3, right? Now, I found my reference angle, and you can see kind of that part of the answer right there. We've also got to figure out whether we're positive or negative in this quadrant. Now, cosecant is the reciprocal of what function? Sine. Cosecant, sine, yep. And sine is positive here and here, and negative here and here. So its reciprocal will likewise have those values. Okay? So that means that, well, let me just fill in some gaps here. So if I have cosecant of 10 pi over 3, that's the same as cosecant of 4 pi over 3, coterminally speaking. And that's the same as negative cosecant of pi over 3 in terms of the reference angle. So the value of the reference angle is that I can kind of reduce my trig function to being taken of an angle that's between 0 and 90 degrees, or from 0 to pi over 2 radians. And I just combine that with the fact of what sign, whether it's positive or negative, depending on which quadrant I'm in, is the idea. So that's the basic setup. Now these were related to some of the symmetry identities. So I mean, there are ways that we could have related it to those. I'm not as interested in that. But yeah, I mean, it kind of breaks down into the fact of, like, you could have realized, oh, pi over 3 plus 3 pi over 3, or plus pi, sorry, is equal to 4 pi over 3, right? kind of taking this but rearranging it. And using one of our trig identities, the symmetry identity, which one is it? This one, I guess we'd relate it to the one with sine, but I could have said that sine of a plus 180 times, oh, that's not a 0, times 2k minus 1 is equal to the negative sine of angle A. So what I would have been able to kind of use this as is if I say, well, sine of this part is kind of like this, right? So I could have said sine of pi over 3 plus pi by this, right? I'm adding an odd multiple of pi, right? 1 is an odd multiple of pi, would just equal negative sine of pi over 3. And since it works for sine, I can then combine the reciprocal identity and kind of get it to cosecant version as well. But I don't think using these for anything other than verifying trig identities or doing work on that end is actually all that helpful. The easier way to approach these problems is just to use your reference angle and the polarity of it based on the quadrant is the easier approach. So that's, I'm comfortable with you using that technique there. But I just want to point out it does kind of relate back to this symmetry identity, which we proved it true, so, you know, basically that means we can use it.
Will we do an example of just like finding the reference angle? And have we already done that?
Yeah, that was, we did a lot of that in the previous course.
So these problems won't necessarily we won't necessarily be tested on them?
Well, you need to know how to get from here to here.
Right, but
but using this bottom technique here, I'm not as interested in. Yeah. But we do need to still know this because this part might come in handy for some other problems. But let's look at these later problems. These ones are actually going to be way more valuable for us in the long run since we already kind of knew how to do the other one using our older technique. Problem 45 says cotan of theta over cosine of theta. All right, and what they asked us to do was to simplify each expression. So I want to try to, you know, write this in as few things as possible is what I'm kind of looking for. And oftentimes, a strategy we might use, this is a possible strategy, is rewrite everything in terms of, let's see, where did my pen just go? In terms of sine or cosine. Oh, I'm getting a little bit of lag here. Is it going to show up? That's funny. Guys, uh-oh, it's thinking. Oh, pinwheeling. No, there it goes. Up, oop, up. There we go. Or, O-S. There we go. Haha, we did it finally. So what I want to point out is that I'll rewrite this problem if the computer will still let me. Cotan theta, sorry, over cosine theta. I'm going to rewrite some of these. So for instance, cotan theta, how could I rewrite that in terms of sine or cosine? Which identity is going to help me do that? Pythagorean identity would be helpful if I had a cotan squared. And actually, even in that case, that would only write it in terms of cosecant. So what trig identity would rewrite cotangent in terms of sine and cosine? Yeah. Yeah, that's one of the quotient identities there. All right, so one of the quotient identities. So I'm going to replace the cotan part with the cosine over sine is essentially what I'm going to do. So I'll have cos theta over sine theta, and then a big all over cosine theta. Okay? And let's see, dividing a fraction by cosine theta, I could view that as cosine theta over 1 and multiply by its reciprocal. So what's the reciprocal of cosine theta over 1? 1 over cosine theta. And what cancels out here? Cosine theta, and I get 1 over sine theta. Wait a minute. I think I can... This isn't quite as simplified as I could get it because I have a reciprocal identity that says cosecant theta is equal to 1 over sine theta. Right? So I could therefore replace this with cosecant theta, so equals cosecant theta. So what I want to point out is this is viewed as simplest form or simplified because this original one had 2 trigonometric functions in it. This one was like 1 over a trigonometric function, but it's easier to just have plain old trig function there, is what the idea is there. Question?
Will we have to memorize these for the quiz, or do we have to...
I'll let you know which ones I'll need you to have memorized at some point, but probably not for this quiz. And it won't be all of it. All right, take a look at 47 here. This one's actually going to require some older skills of ours. I have squares of binomials here. And you might recall that a, actually plus or minus b, all squared, is equal to a squared plus or minus 2ab plus b squared. So if this is a minus sign, then this is a minus sign. If this is a plus sign, then this is a plus sign. There's my square back. Bam. So I'm going to expand this, is my plan. So in this case, a is sine x and b is cosine x, and I'm going to expand this. So I'm going to expand it to a squared plus 2ab plus b squared. So sine x squared would be sine squared x plus 2 times sinx times cosx, right? Plus cosine squared x. Right, so that's the first part expanded using this pattern. And this pattern is from back in the days of Algebra 2 or Math 3, whichever you called it. So let's see, now let's expand this other one. So that one's going to be sine squared x minus 2 sinx cosx plus cos squared x. And if you didn't memorize that pattern, you could also have accomplished by multiplying this by itself, which is what squaring after all means, and then either distributing it by itself or foiling it by itself there. So, friendly friends, notice some of the things I can do here. What happens here? Yeah, if I try to combine those like terms, those will actually cancel each other out. And I could combine some of the other things here first, but I actually don't think it's necessarily that helpful to just yet. It would add a little bit of work. But because I do have multiple sine squared x's and multiple cos squared x's. But I think that this and this I could combine to be something. It's one of my identities. I know that sine squared x plus cos squared x is equal to 1. That's one of my Pythag identities. So I could replace both of these with a 1. Plus this guy and this guy is another 1. And 1 plus 1 is 2. You plus me equals us, right? This is a quote from a song back in the day when I was in high school called I Know My Calculus. Actually, no, I think it was maybe when I was still a high school teacher then.
Is that like one of the ones you
Apparently, not, I would, no. I mean, if I had a pickup line, I'd say something more to the effect of like if a girl was a cute angle and I'm a cute angle, let's get together and be all right. You know, because I'm a, like, if that would of course be if I was a complementary angle, which I suppose I might compliment. You know, back in the day, maybe I would have done that. Yeah. So let's look at one more example here. So So here we go. This one's another one where I'm multiplying binomials of trig identities, or trig functions rather. So I'm going to just FOIL this out. All right, so I'm going to multiply the 1 times both of those, and then the cosine by both of those. That's my plan. So let's see what we get. Equals, multiply 1 by both of those. That would be cosecant theta minus cotan theta. And then multiply cosine by both of those. That would give me plus cos theta cosecant theta, right? Minus cos theta cotan theta. Interesting. Now, yeah, isn't this beautiful? Yeah, that's good stuff. So let's see. Now I've got some options. Now I'm not leaning towards using any Pythag identities just yet, and I'm avoiding them right now because I don't see any squares. Right? I don't see any perfect squares anywhere. Pythag identities are usually all based off of squares of things. So I'm steering away from those. I'm thinking I might be able to do some interesting stuff with this guy, maybe, and maybe this guy, perhaps. I'm interested to see what happens in those. So I might actually go down the route, and I'm just gonna and that's how some of these problems are, where you just start kind of like picking at it, like work a little bit in one direction, see if it's helpful. I might end up coming back to these guys and possibly I might just end up rewriting all of these in terms of sine and cosine. But we'll see. We'll see. First thing, cosecant, I'm going to replace that with 1 over sine theta. And cotan, is this going to be helpful? I'm trying to think. If I rewrite that cotan. What do you guys think? Should I try it? Let's do it. Let's replace this guy with that, and this guy with that. Should I just go all the way? Yeah, let's just do this. Yeah, let's just write all of it in terms of sine and cosine, see if that helps, right? And I'm just kind of like picking at it, moving in one direction, see if this is going to do anything good for us. So cosecant theta is the same as 1 over sine theta minus cotan theta is cosine theta over sine theta. Yeah. Plus cos theta times 1 over sine theta. I'm wondering I might not have wanted to do this one here, but we'll see what happens. Minus cos theta times cos theta over sine theta. So let's see if this helps us any here. Equals. Now, all right, so I'm going to want to pick this apart a little bit. This part here is the same as what? Cosine over sine, yeah. Actually, you might even though these aren't super obvious, I could have rewritten this as cosine over sine. It's a positive number of cosine over sine. Here's a negative cosine over sine. Those are just going to cancel each other out, right? Or I could have even rewritten this as cotan theta, and if I'd left this one as cotan theta, they still would have canceled each other out. All right, do you guys agree with that? Yeah. So let's see, and then over here, I'll leave this as 1 over sine theta for now, minus, what does this one become?
Just sine.
Yep. Okay. Multiplying it by it, right? You could put this over 1 if you want, just multiply across. That's fine. Okay, this is interesting. Now, hey, these have a common denominator. So I could rewrite this as just 1 minus cos squared theta all over sine theta, right? And guys, I'm seeing a cos squared. The minute I see any trig function squared, I am immediately thinking of which identities? Pythags, right? What is the Pythag identity that has cosine in it? Right. So I could possibly replace, try to find a way to solve this for cosine and do that, right? Plug it in there. Or I might realize, wait a minute, 1 minus cos squared theta. If I subtract cos squared theta from both sides here, I'll get a 1 minus cos squared theta here, right? So there's a few different ways you could do this. The manipulation is kind of all up to you. But if I subtract 1 cos squared theta from both sides, that's an S there. Sorry. So let's see. So sine squared theta is equal to 1 minus cos squared theta. Yeah, it does. But anyways, so guys, this is what I would call a modified Pythag. All right, where in order to have this be useful to me, I had to do a little bit of manipulation to it, so to speak. And I'm claiming that 1 minus cos squared is equal to sine squared, so I should be able to replace this whole part with sine squared, right? It works out. It works out. Not the only way you could have done that. So this is the same as sine squared theta all over sine theta. What happens there? This sine theta cancels out with one of those, leaving one behind. So I get plain old sine theta. Okay, so as I said, you just kind of have to start picking at these sometimes and try to figure out what's going to be helpful. Like for instance, I changed this one and maybe changing it wasn't that helpful. I don't know. But it all worked out. And then, the modified ones are the really interesting ones where you end up having to somehow tweak one of your identities slightly in order to get it to work. But there's clues. Like I said, I saw the square, so I started thinking cosine squared. I was thinking Pythag. And I saw that with a little bit of change and rearrange, I could make it work. So anyways, so thanks for watching, friends. Have a great day. Bye-bye.